Hello everyone. First of all, thank you to the organizers for letting me present my work here. Today I'm going to present a work that is based on gaseous detector 2, similar to the one that Lucas did and Hannah did, and also Thiago, but it's focused on low energy applications, so the detection of fluorescence X-rays. So just a summary, I will talk about the energy resolution limits that we have. Then I will talk about the escape probability and escape peak issue in our detector. Uh, After that, I will talk about the background contamination of copper that we have. And in the end, if I have enough time, I will show a readout time model and also a flat field correction that we have made. Okay, so just a very quick introduction. This is the gem detector. So it's a gaseous detector which has a active region here. So this is where the ionization happens. And the charge that are created here in this active region, they're going to drift towards the gem. And inside the holes here, they're going to be multiplied. So uh, in the end, we can collect all these electrons from the multiplication here in a readout system, and then we can reconstruct the position of interaction. So this type of detector is widely used on high energy physics experiments. So it's mainly used on TPCs, but now we want to use these detectors also in low energies experiments too. So here's is just one example of the things that we can do. So here is four different color pigments that we study. And here we can see the image, the reconstruction image of these four pigments. The colors here, they are somehow proportional to the energies of the fluorescence of these elements that compose the samples. And here we can see a more detailed vision about the energy spectrum for each one of these pigments. So one thing that I just want to your attention here is that for each line, each principal line that we have here, we also create a small peak here. This is the escape peak that I'm going to talk about later. But we are able to detect the major components of each one of these elements in these pigments. Okay, so since we want to detect the large amount of elements, the first thing we want to see if we have a fair energy resolution inside our detector. So to study the best possible energy resolution that we could achieve, we have made some simulations using HEAD and Garfield++. So Garfield is a software that is specialized in gaseous detector simulation, and HEAD is the one which make the interaction of photons inside the gaseous medium. So here you can see what you can see is the number of primary electrons which are created by 6 keV photons. So the photon is going to interact here in the active region and is going to create a specific number of effects of electrons, sorry. So here you can also see the argon escape peak. And we can see that we create something close to 200 electrons in each one of these events. So now if we make the charge multiplication, so if we let these electrons to drift here towards the gem and we collect them in the end. So here what you can see in the right is the number of electrons which are created by each primary electron. So This is the histogram of the number of electrons after the multiplication for each one of these electrons here in this active region. So here we have the number of electrons for different potentials applied between the gem foil. And now we can make a very simple Monte Carlo simulation where we are going to draw here, respecting the probabilities, a specific number of electrons. And what we can do the reconstruction. We can create the energy spectrum after the multiplication. So here, what we have is an energy spectrum without any noise, without any electronic issue. And when we compare these simulated data with what we have inside our lab, this is the experimental result of the iron 55 energy resolution. Oh, sorry. So we are working pretty much close to the best possible energy resolution that we could get. Okay, now talking about the escape peak issue. So the escape peak is created when part of the energy is not completely deposited inside our detector. So we are going to have a photoelectric effect here. And then this photon, which is created by the transition of these electrons, this fluorescent photon, which is the fluorescence of the gas. So in the case here, argon, this photon can escape from the active volume of our detector, and we will not have the complete energy of an event. So what we made was another simulation to scan the dirty region here, the active region, and with this scan we throw 10,000 photons in each one of these points here, and we calculate the probability for this photon to the mean probability for a photon not to interact inside this dirty region. So here what you can see is this escape probability. So for three different detector setups. So the first two, this one and this one, is the detector operating with argon CO2, but with different drifty region thickness. So this is for 1 centimeter and this is for 3 centimeters. And you can see that increasing this active volume, we can decrease a lot the escape peak height. And also we have another simulation where we use krypton, which is a good candidate too, because it's not going to produce a energetic fluorescence photons. So the fluorescence for krypton until 15 keV is just 1.6 keV. So this photon here is much likely to be trapped inside the detector. Okay, so now talking about the background contamination that we have. So I showed you before this energy spectrum for one of these yellows here. This is the chromium yellow. And when we look at the energy spectrum that we could make with different detectors. So here's a energy spectrum using a silicon detector. We can see that we have the chromium peaks here, which are presented here. We have the lead peaks, which are all together here. But we also have a copper peak here, which is not presented on this spectrum. So why does this copper peak appears? It appears because we can have fluorescence of the copper, which compose the gem foil. So the primary electron can come here and does not interact in this dirty region, and then it's interact here in this thin copper foil that we have, and then it creates a fluorescence photon. So we can calculate the contribution of this fluorescence peak, which appears inside our detector by using this expression here. So we are going to have a term which is proportional to the primary beam absorption, then the fluorescence absorption by the sample. And we also have to take into account different things. I'm not going to enter into too much detail, but another thing that we have to add is also the probability to absorb this fluorescent photon inside the drifted region. So we have to add this term here. And also we have to add some terms which are related with this beam absorption before it interacts inside the detector. So we have to take into account the window transmission, the air transmission, and also the drift transmission. So if we integrate over all the copper layer and over the phi angle, what we get is this final integral here, which we can solve this numerically. So here's just a example showing the contribution for the contamination by different parts of the detector. So in green here, you can see the top gem electrode, then the bottom gem electrode, and also here in red, the readout contamination. So the readout is also made by copper, and it's going to produce two a contamination. So we can then integrate over all this copper that we have here. And what we get is this result. So here in magenta, you can see the contamination detection probability. So the probability to detect a contamination for two different geometries. So this one here is a 3 centimeter drift region, and this one is for a 1 centimeter drift region. So we can see that if we increase the drift region, we also increase the contamination that we can detect inside our detector. However, if we get the number of primary electrons that we could detect with this drifted region and divide by the contamination, we can see that this ratio is much more it's much more it's much more likable to be used a drift region which is larger, because we also increase the probabilities to detect higher energy photons. Now,
Giovanni, 3 minutes.
okay, so now another thing that I want to show is just the same result, but if we change this copper cladding here. So if we change this copper cladding for aluminum, what we get is these two curves here, and we can see that the total contamination that comes only from the readout. Here we kept the readout using copper. So we can see that we are able to decrease a lot the contamination inside our detector if we change to aluminum. So now just to finish, we have made a toy model to study some artifacts that are showing our, that can be seen in our image. So I'm not going to enter in too much detail, but one thing that we can see that is we are able to collect this chart in a non-continuous way. So we collect chart only in these strips, and what we get in the end is a error in the reconstruction of the position inside our detector. So what does this mean? So it means that in our images we have this readout pattern here. So this pattern, it's a issue when we want to get a reliable value when we are when we want to characterize our detector. So we can see a modulation here which can uh, affect the contrast and the resolution of our detector. And the main idea is that we can reconstruct a correction matrix. I'm not going to enter into much detail, but you can email me a question after that. But we can create a correction matrix using projection histograms. And here in the end, I'm showing you the results. So here's the old image that we have and the projections, so the profiles of X and Y. And after applying this correction, what we get, it's a much more smooth uh, pattern, and this could be very helpful when we want to characterize the detector. So that's it, I think. So just to conclude, with the energy resolution that we have, we can detect uh, different elements which are not neighbors in the periodic table, but which are very close. Krypton will reduce the energy spectrum population in terms of the escape peak. The aluminum gems can be an alternative to reduce this copper contamination, and this flat field correction, which can be applied to other types of detector too. It's a nice tool to improve the image quality and also the detector characterization. So that's it. Thank you.
Thank to you, Giovanni. We have a question on the chat by Marcia. Is is asking if using aluminum may help improving resolution.
Well, I don't think uh, it's going to change a lot the resolution. I think that the resolution is more likable to be affected when we change the readout system. Uh, but I don't think these aluminum foils, they are going to change the resolution. One thing that we know is that these aluminum foils, they can oxidate over time, and we will have to study how this oxidation is going to affect the operation of the detector. But in terms of position or energy resolution, I don't think it will affect the resolution.
Giovanni, the idea of the aluminum is to avoid contamination and so remove this unwanted copper peak in the middle of the scene. Just that.
Yes.
Yeah, okay, Matthew was referring mostly to energy resolution.
Okay. Yes, to the energy resolution, I think the main change is going to be the gas that you use. So yeah, we are limited to the resolution of the gas that we have. So I think this is the answer. So Tiago also has a question.
Tiago, wait, please.
Hi, Giovanni. Nice work. Thank you. I have a question concerning this aluminum idea. I mean, this is obviously to remove the copper contamination from the spectra, but would you expect the aluminum K alpha photon to affect somehow your measurement? This low energy photon will not appear in the spectra, but can increase the noise, electrical noise in the detection of the systems. Do you expect some effect regarding this?
So I don't think so too, because well, one thing that we have, and we know that we have, is the we already are detecting copper contamination, and it doesn't affect too much the acquisition. But also, I think if we take a look very quickly in the energy spectrum here, so the aluminum escape peak, I think, is going to be close to 1 keV, and we cut this by electronics. So I don't think we are going to be able to to see this. It can affect somehow, maybe if you have a large amount of countings inside our detector. So if you have pileup and stuff like that, maybe these aluminum fluorescence can be taken into account wrongly, like in other interaction too. In other event, it can pile up, but I don't think it's going to be a huge problem or a problem at all.
Yes, but concerning this random combination between different photons and this aluminum K alpha, could this damage resolution? Just the last question.
Well, we have to think that we have a peak here, which is in the middle of our energy spectrum, and it doesn't affect that much. So aluminum is not going to be here mixed with all of these, and so if this copper peak is not an issue in terms of position resolution, maybe aluminum is not going to be true. But I really don't know. We have to test this.
Thank you.
Johnny, we have a last question by Marcia, if you can reply very quickly. So what kind of gas may help in increasing energy resolution?
We have to take a look in the number of primary electrons which are created by a same event in different gases. So what we want to increase the amount of primary electrons that we have. So a good gas would be a gas which has a work function that which is not too large. So we want to increase the number of primary electrons which has in this spectrum here. So in terms of different gases, if we take a look into the noble gases, they are going to have pretty much the same energy resolution. So I have made this simulation here for krypton, for neon, and they have pretty much the same resolution in this energy range. So if we want to use a noble gas, we are limited by this the same energy resolution. I'm not sure if we have some different, very much different types of gases use it. I don't think so. Most of the works, they use a noble gas mixture with another thing, but it's I don't think we can change that much in terms of energy resolution because we are limited to this number of electrons, and we are limited to the gas. So
thanks a lot, Giovanni. So let's greet again Giovanni, but all
thank you.
With the presenter of this session. So